Okay, today we're going to be talking about ratios and proportions. This is something that you may or may not be familiar with. I don't know, but is going to be extremely useful, especially when we move into Algebra 2, Pre-Cal, Calculus, etc., because it's going to allow us to solve equations. Because now we're taking what is known as a ratio, which is a comparison of two numbers or expressions. They don't have to necessarily be numbers or quantities, and they are measured in the same unit. So they have to be the same units of measure. So there's two different ways to represent ratios. I can either represent ratios, well, three ways technically, A to B, so with words, the ratio of A to B, or I can represent it as a fraction, A to B, ratio, fraction, or I can represent it like this, with a little colon, A to B. Now, obviously, since one of the representations is a fraction, that denominator can't be 0, right? If the denominator is 0, it makes this undefined, because you can't divide by 0, right? So there's two things that I should point out. The first one is if we're dealing with fractions, we have to keep in mind that we want to write them in simplest form, at least at the end of the problem. But if we can simplify a fraction, that allows us to work with smaller numbers. So if I give you the ratio of, let's say, 7 to 14, I can represent it like that. I can represent it as a fraction, or I could represent it in this format. But if I had a fraction, I'd want to go a step further. And what is each the numerator and denominator divisible by? 7, right? So if I divide the numerator by 7, I get 1. And if I divide the denominator by the same number, I get 2, right? So we do want to simplify. Now, we say that two fractions with the same simplest form, so in other words, if I take two fractions and I simplify each of them, that they are called, do we know? Equivalent fractions or equivalent ratios. So 7/14 equals 1/2. If I give you 2/4, that's also equal to 1/2. So 7/14 and 2/4 would be equivalent fractions because they both reduce to 1/2. Now, what if we looked at some examples of ratios? Let's say the number of girls in the class to boys in the class. Well, how many girls are in here? Can you tell me? How many girls do we have in here? 6? Six plus 3, so we have 9 girls in the class. How many boys we have in the class? 6. Is that in simplified form? No, we could reduce that to what? 3/2. Okay, good. How many students do we have in total? 15. And there's one of me. So we can see how we can represent our units are people in the first one, and same with the second one. So that's the same units, it's people. And if I look at the third ratio, I see a ratio of feet to inches. Now remember, we want to have them in the same units. So we would have to convert either both to feet or both to inches. Well, since the denominator is not even a foot, maybe we'd want to convert it to inches. How many inches are in a foot? 12. So how would I represent the numerator in terms of inches? So it would be 36 inches to 2 inches. And then if I wanted to simplify that, what would it be? 18/1. Okay. And you will see, especially when you get into algebra 2, that we do want to have in terms of a unit ratio. So the denominator is 1. Like, think of when you're the speed limit, right? They say 36 or 30 miles per hour. They don't say, for 2 miles or 2 hours or something. All right, so let's go ahead and look at a geometric example. If I look at this, I see the width, and I see the length. So if I wanted to write a ratio of the length to the width, how would I write that? The length would be 15. The width would be 6. They're both in centimeters, so we're good. Now, if I wanted to write that as a ratio, as a fraction, this would be 15 over 6. Is that simplified? No. What is the numerator and denominator divisible by? I can divide each of them by 3. And remember, to keep it an equivalent ratio, equivalent fraction, I have to do the same thing to the numerator as the denominator. Okay, so, because this is like 1, right? 3 over 3 is just 1. So if I simplify this, what am I going to get? In simplified form, it would be 5 over 2. Good. Simple. Right? Let's look at another example, but they get a little bit more interesting. We have a rectangle. So my rectangle is A, B, C, D. And I know the perimeter of the rectangle is 60 centimeters. Remind me how we would find the perimeter of a shape? Add up the length of all the sides. Exactly. Now, I'm being told that the ratio of AB to BC is 3 to 2. So I can say that this is 3x and this is 2x, because the ratio is 3 to 2. In simplified form, it may be, a multiple of that. So if that's 3x, then this is 3x. If BC is 2x, then this is 2x, right? Because this is a rectangle. So the opposite sides are congruent. Now, we know that the perimeter is 60 centimeters. So I know 3x plus 2x plus 3x plus 2x equals 60 centimeters. So if I combine my like terms, all my x terms, 3x plus 2x plus 3x plus 2x, how many x's do I have? I have 10 x's, and I know that that equals 60. So then how would I solve for the value of x? I would divide each side by 10, and I'd get that x equals what? 6 centimeters. Okay? Now, I am being asked to find the length and the width as well as the area of the rectangle. If x is 6, then what is the length? How did you get that? We found x to be 6, so I just multiplied 6 times 3, and I got 3 centimeters. So the length is 8 centimeters. And the width, similarly, since I found x to be 6, multiply 2 times 6, and what is my width? 12 centimeters. But then I'm also being asked to find the area. Remind me how I find the area of a rectangle. It's length times width. So that means I have 18 times 12, which is what? Now, let me ask you this, because we want to write units of measure. What is the units of measure for area? So it's, in this case, centimeters squared, right? Good. All right, let's look at another example. We have a triangle. My triangle is J, K, L. And I have an extended ratio. Do you know what an extended ratio is? Well, an extended ratio just means, oh, goodness gracious. An extended ratio means I have 3 or more numbers, right? So there's my extended ratio. Now that corresponds to our angles, right? Because we're looking for the measure of angles, and the measure is given as an extended ratio. So J is 1x. Let me go ahead and make this, I want to use a different color. I'm a little neurotic with my colors. My mother laughs at me. So J is 1x. K, which was the next one, is 2x. And L is 3x. I want to find the measure of the angles, so I have to find x. What do I know about the sum of the interior angles? Okay. So I set up a nice little equation. Combine like terms on the left to get 6x equals 180, so x equals 30 degrees. So I can now find the measure of angle J is what? 30 degrees. The measure of angle K is 60 degrees. And the measure of angle L is, well, they gave us J, K, and L, right? It doesn't matter how you draw it. This is not drawn to scale. Excellent question, Georgia. It doesn't matter. Because you know, had I known, I would have made L where K is, because it's 90 degrees, right? Based on the way I drew it. Jackson.
I did something similar, but I think they did it a bit differently.
What did you do?
I just added 1 to make it get 6. I divided 186.
That's exactly what we did here algebraically.
Okay, never mind.
Right? No, you are correct. You did it absolutely, but you see how we wrote it algebraically. I want y'all to get in the habit of writing out these equations and solving these equations, because next year's all about writing equations and solving equations, crazy equations. So let's get in a good habit of showing the everything. All right, moving on. So we know a ratio is a little fraction. What is a proportion? Well, a proportion is just an equation that states that two ratios are equal. So a ratio set equal to another ratio is a proportion. Now, do we necessarily look at just numerical values in these ratios? No, the whole point is we use proportions to solve equations when we're trying to find the value of an unknown. So the numerator of one thing contains a variable that we're solving for. So if I know that the two ratios are equal and I have a proportion, I can use some beautiful properties to allow me to solve for them. So that's the whole point of knowing these properties. So here I have two ratios. AB is equal to CD. So we say that A is to B as C is to D. I can rewrite them in terms of these little colon notation. But some new terms that you may not be familiar with are things such as extremes and means. So given a proportion, the extremes are these values. Those are known as your extremes. Why? I have no clue. But one way I like to remember it is written in this format. They're the ones on the outside. They're the extreme ends of this entire equation. So that leaves us to other values, which are known as the means. Now, we'll see where this comes from when we start talking about, have y'all talked about geometric means yet? No. Okay, we'll see that a little bit later, why that term is used. So if I were to ask you, if I were to give you this proportion, and I asked you what are the extreme values, you would say A and D. And therefore the means would be B and C. So we have to be able to use those terms with ease when describing properties. So let's go ahead and look at some properties of proportions. And again, you're using the names, but this will just be some things that will be like human nature to you, natural instinct to use these properties without names in Algebra 2 and so on. So the first one is known as the cross products property. And you may have seen this. So if you have a proportion, a ratio set equal to a ratio, and you are looking for the product of extremes setting equal to the product of the means, that is what's going to allow you to perhaps later down the road solve for an unknown. So here I have my ratio. This is true. These two ratios are equivalent. This proportion exists if and only if AD equals BC. So where have you seen this maybe? When you cross multiply, right? That's just cross product property. Product is multiplication. And again, the denominators can't be 0 or this isn't defined. So if I want to verify this is a true proportion, that these two ratios are equal, all I would have to do is multiply 7 times 8 and see if that equals 28 times 2. Now, let's say you looked at these and you say, oh my goodness, I don't want to have to multiply those numbers together. Is there something I could have done to make this problem easier? I mean, you would get that these two are equal. You'd get an identity, so therefore they are equal. I would. So if I were to reduce the first fraction, what would you get in simplest form? Okay, and look at the next one. So we know they're equal, right? 1 times 4 equals 1 times 4, but I mean 1/4 equals 1/4. So depending on how large these numbers are, or how complicated the numerator or denominator is, we may want to simplify before we start working the problem. Second property of proportion. Oh no, let's do an example where we actually get to solve them. Oh yay. Okay, so I'm going to look at the product of my extremes. So I have 30 times 3m minus 5, and that's going to equal the product of my means. And does it matter whether I write 10 times m plus 1 or m plus 1 times 10? No, the commutative property of multiplication says the order doesn't matter. I like to write it in this form because then I can easily see I need to distribute. So if I distribute the 30 to each term inside the parentheses, what is my new binomial on the left? Multiply, multiply, multiply. Excellent. And if I distribute on the right-hand side, what am I going to get? Plus 10. Now, I'm obviously solving for the variable m, so I need to get all my terms with m's on one side of the equation, the constants on the other, and solve for the value of m. So I would go ahead and subtract 10m here. It doesn't matter. You can move the 90 to the right-hand side of the equation by subtracting, but you might be making a little, you know, a little bit more room for error with minus signs. Okay, so this is going to give me what if I perform these operations? What's on the left-hand side? Mm-hmm. Excellent. And then what would I do to solve for m?
Divide by 80.
Beautiful. And so therefore m equals 2. And I could substitute m back into the original proportion and make sure I get a true proportion, two ratios that are equal. You want to try the next one and see if you can get it on your own? Sure, try it. You do it, I do it, and we see if we get the same thing. Don't look. Do it on your own. How many people got y equals 6? Yay! If not, make sure that you see how to get y equals 6. And again, you know, down the road, you're going to want to check to make sure your answers are correct. But, you know, maybe you have faith in yourself at this moment with your arithmetic. All right, let's look at some more examples. As part of word problems, as part of a science project, you need to estimate the number of blue spruce trees. So this is what I'm trying to do. I'm trying to estimate the number of blue spruce trees in a 50-acre forest. So I'm looking at the number of trees, oops, in a certain acreage. So trees per acre, right? Maybe is a ratio that I would be interested in. You count that there are 36 trees. So there are 36 trees. In how many acres? In 3 acres. So do you see my ratio of trees to acres? They gave me that. That's given information. I have 36 trees for 3 acres. I'm trying to estimate the number of trees. We'll call that X or T, it doesn't matter. In 50 acres. Does everybody see how I set up this proportion? Okay, so I'm solving for X. Remember, I'm going to use the product property, so the cross product. So I'm looking at the product of my extremes, and I'm setting that equal to the product of my means, and I'm solving for X. So if I multiply on the left-hand side, what am I going to get? Okay, and that's going to equal 3x. So my next step would be to divide each side by 3, and I get
600.
X equals 600. Now this is a word problem. So I'm being asked to estimate the number of blue spruce trees in a 50-acre forest. So I would say there are 600 blue spruce trees in 50-acre forest. Yes, sir.
No, isn't it 1,800? There's only
Doc-
X.
No, I saw for X.
Dr.
The number-
P,
Yes,
couldn't you have just simplified it to 12 over 1?
absolutely. Absolutely.
Wait, it's simple.
So I could have, that is fantastic that you noticed that. I could have taken this and said, okay, divide each of them by 3. And then I'd still multiply and I'd get X to be 600. Do you see why we're saying that there's 650 acres? Because if I were to reduce that, 600 over 50 would reduce to that 12 over 1. Okay, that's our first property. Let's look at our second property. Our second property is the reciprocal property. If 2 ratios are equal, if 2 ratios are equal, I have a proportion, right? But if 2 ratios are equal, then their reciprocals are also equal. So if I have A over B equals C over D, I can take my little numerators and make them denominators. So take the reciprocal of each. When you invert a fraction, the numerator becomes the denominator and the denominator becomes the numerator. That is taking the reciprocal or inverting the fraction. So if I take the reciprocal of each of them, they're still equivalent. Why? Because these 2 numbers are equal and they're still equal, and these 2 numbers are equal. So I can invert both sides. So for example, if I have 2 over x equals 5 over 8, I can also write this as x over 2 equals what? And if I wanted to, I could solve for x, right? Here it would be 16 equals 5x. Here it would be 5x equals 16. I know the 2 sides of the equation are equal, right? It's a balanced equation. Oh, but then what would I do? I'd have to divide by 5 and I'd get a nice little improper fraction, and you should never fear improper fractions. You will see those a lot in Algebra 2. Okay, so that's just the reciprocal property. If it's easier to work with, you can just take the reciprocal of both sides. Now, there is another property, and that allows you to interchange means. So if you interchange the means of a proportion, so I know that the 2 fractions are equal, the 2 ratios are equal. If I interchange the means, you still get a true proportion. It's still a proportion. So if you have 6 over 8 equals 3 over 4, and I interchange my means, what am I going to get? I'm going to get 6 over 3 equals 8 over 4. So while I can multiply in this case and get 24 equals 24, I still get 24 equals 24 here. If I wanted to simplify this fraction here, what would it be? 6 over 8. If I divide the numerator and denominator by, let's say, 2, I'm going to get 3 over 4. If I simplify each of these fractions here, what do they become? So do you see how they're still proportions? The two sides are still equal.
Is that because whenever you flip it, it's still
Invert it.
Yeah, whenever you invert it and you cross multiply, it's still equal to the same thing.
Exactly.
Wait, why can't you do that with the extreme?
Why can't you do that with the extremes? Well, because then you're not, it's not necessarily true in that case. Can it be? Yes. Is it always? No. And we could show that, right? Because 4/3, well, in this case would be 4/3, yes. But you're changing from an improper to a proper fraction, perhaps at sometimes. So this one is definitely true. Okay, interchanging means. Now, the fourth thing that we want to take into consideration, and remember when working with proportions, is in a proportion, if you add the value of each ratio's denominator to its numerator, then you form another true proportion. So let's say you begin with this original proportion. And notice what we're doing. We are adding the denominator to the numerator. We are adding the denominator to the numerator. I still retain the fact that the two sides are equal. So let's look at this example. This one says 5/6 equals 15/18. If I add 6 to the numerator here, what am I going to get? 11/6. If I add 18 here, what is my new numerator? And are those two equivalent? Yes, they are, because if I simplified the right-hand side, in other words, if I divide the right-hand side by 3 in both the numerator and denominator, what do I get? Oh, that's nice. Again, it's not so much that you know the specific properties in and of themselves, it's that down the road you're going to need to use these. These are going to be useful tools for us.
So like for that one, you would multiply to then find something that it could like.
Right. I mean, let me just explain. Down the road, you are going to have a beautiful type of function that involves ratios, and maybe one part of the ratio, the numerator or both, denominator, is a nice long expression, x cubed plus 4x minus 2. I mean, you're going to have to do some great work. You're going to have to factor, you're going to have to simplify, then you may have to cross multiply and solve for the values of x. I mean, these get good. They get good, but we need to be able to manipulate them with ease. Okay, so let's look at each of these and tell me, is it true or is it false? And if it's false, what would we have to do to make it true? Okay, so if I look at this, if I multiplied, right, is this true or is it false? Well, if I could just interchange my means here, I would get P over R equals 6/10, wouldn't I? So is P over R equal to 3/5? Well, if I simplified the right-hand side in the first one, dividing both the numerator and denominator by 2, what do I get? So this is true, right? What about the next one?
That one's false.
Why?
Because they added 3 on the second equation, they should have added 3.
That's right. So this should have been, so this is false. it should have been a 4 here, right? Now let's look at let's put some of this stuff together and see what we can do with these triangles. Okay, in this first example, I see, okay, let me look at the components. Let's see what I've been given. I've been given 4 over 2, so 4 over 2 equals 6 over 3. So I could say 4 plus 2 gives me what? 6 over 2 equals, and what am I going to add to the second one? 3, which gives me 9. And is that a true proportion? Yes, the two sides are equal. They both reduce to what? Okay, let's use the property of proportions in the next one. Okay, so I have that MN over RS so I'm going to write those values down because I see them. So I have 8 over what? 10 equals NP which is 4 over ST which is 5. Is that a true proportion? Yes. So let's go ahead and use the properties and the given measures that we've just given to write 4 true proportions. So if I think back to the properties we just looked at, well, let's think about them. We did cross product. That was 1. Then we did the reciprocal. That was the second one. Reciprocal. And then we interchanged the means. We switched the means. That was another property we looked at. And then the last one is when we added the denominator. So let's see if we can use these properties to come up with proportions. So for the cross product, I'm saying that MN, so I'm using this here. I'm saying MN times ST, so MN was 8, times ST which was 5, equals what? RS, which was 10 times NP. So we have shown that 40 equals 40. So we've just demonstrated that cross product property. Okay, let's look at the reciprocal property. So the reciprocal property is what? It says to leave the fractions alone on each side numerically, but invert them. So what do I have on the left-hand side? What is the reciprocal of the first fraction? 10 over 8. And that's going to equal what?
5 over 4.
Beautiful. So we've just demonstrated the reciprocal property. The next property is we want to show that how we can switch the means and still have a proportion, the two sides equal. So if I switch the means, what is the left-hand side going to be?
8 over 5, or 8 over 4.
8 over 4. And that's going to equal what? 10 over 5. So I'm just demonstrating the properties for this geometric example, these diagrams. And last but not least, let's talk about the diagram. So we start with our original, the diagram, the denominator. If I start with the original proportion, what am I adding to the numerator of the first fraction? And what am I adding to the numerator of the second fraction? Okay, so what is my new numerator on the left? 18 over 10 equals, and is that true? Yes, because if I divide the numerator and denominator by 2 on the left, I am going to get 9/5. Okay, now let's see if we can use these properties and actually solve for some unknowns. So we're going to use proportions given this diagram to find AD. So I'm looking for AD, which means I'm looking for X, right? And I'm looking for the length of AB. AB is this. So how would I write that as an expression? How would I write AB? Does anybody have an idea? Is it X? Yeah, it is. So this would be X, because the whole thing is X minus 22, because X minus 22 plus 22 is that whole length X. Good. All right, let's see what we've been given. We have that AB, so AB over BD, which is 22, equals AC, which is 27. I'm just substituting in the values I know from the diagram, over CE, which is 18. Can everybody get that proportion from the diagram and the given information? Okay, so I need to find AB. How do I find AB? What property would I use? The cross multiply, the cross product property. That's right, which says this AB.
Could you simplify that?
You can. You absolutely can. You all want to simplify the right-hand side first? Sure, why not? So I'm going to leave the left-hand side alone. So AB over 22 equals what? What am I dividing the numerator and denominator by?
9.
9, okay. So what is my new right-hand side?
3 over 2.
Okay. And then you said multiply AB times 2 equals 22 times 3. So AB, I'm going to use my green. Times 2 equals what? 22 times 22.
66.
66. And then what would I do?
Divide by 2.
Okay. So that means AB equals
33.
33. Ooh, look at us. So AB equals 33. Now I'm looking for AD. How am I going to, I know this equals 33. Okay, so 33 plus 22 is 55. So AB we found to be 33. 33 plus 22 gives us our 55. Now you may be saying, well, why did we write the x minus 22? I was just seeing if you could algebraically think of an expression that represented that in terms of what we knew. Now, in the next lesson on Tuesday, we are going to be talking about scales, similarity, etc. So this is a little foreshadowing, and we will review it on Monday. So a scale drawing is a drawing that is the same shape as the object that it represents. The scale is in fact a ratio that describes how the dimensions in the drawings are related to the actual dimensions of the object. So if you notice, you may have seen these before where you're like, ooh, I have this triangle and I have this triangle. Well, one may be a scale of the other, and I would be able to write a ratio to the sides, right? So for example, where we see that in the world is a map. A map is a scale drawing. So if I have two cities that are 96 miles from each other, so I have two cities and they're 96 miles from each other, but on the map, the cities are only 4 inches apart. So while this may be 96 miles, it is represented in terms of 4 inches. Does that make sense? They're obviously not going to put 96 miles on a map. You never have a map big enough to do it. So they put it in a little scale. So if I want to write this as a ratio, perhaps of miles to inches, my ratio would be 96 to 4. So that would be my ratio. So what is my scale? So this is the ratio, but now let's look at the scale. Now, normally you just divide so that you have 1 in the denominator. So if I divide the numerator and denominator by 4, what am I going to get? 24 over 1. And this would be referred to the scale. So for every inch on the map, it represents 24 miles. So on the map, 1 inch represents 24 miles. Does that make sense? Kind of neat. All right, so you have homework on 7172 in your packet. You are welcome to spend the rest of the period to do that. It should go very quickly, and you can work with your math friends. On Tuesday, we will do 7.3, and then what's happening on Thursday? There is a quiz, and the quiz will cover everything we've done this week, 6.4, 6.5, 7.1, 7.2, as well as 7.3. So it will include Tuesday's notes. But you are welcome to work on your homework now.
Can we log off?